So welcome to the fourth class of this particular course, and just to revise it, the last class we have gone through some basic physics related to the field ionization of the gas atoms and the tunneling process. What are the critical things needed for the electron to tunnel through the gas atom towards the metal, and those two critical things are the electric field applied, which increases, which makes the minimum potential energy near to the Fermi energy of the metal surface or the metal tip. Then the X critical, where the which is if it goes less than the X critical, the repulsive forces will takes place. So your tunneling process cannot happen. So it should be at less near to the XC or more than that, so that the tunneling process can takes place. And we also see some examples of the FIM images where the gas atoms are actually which are imaging gases, those get ionized on very high positive voltage when applied to the tip, and these gas ions accelerates towards the phosphor screen, and it hits to the positions, and those positions are nothing but the atomic terraces which are found on the atom probe tip. So the next question is how to so what is the magnification what we are getting through this field ion imaging. Fine. So we as I told you, the bright spots on the film are nothing but the place where the atoms are located on the tip surface. Now you can clearly visualize these atoms on the film images. Okay. So there is a certain magnification is associated with that. Fine. So you in the atom you cannot resolve those atom in your atom probe tip, you cannot resolve the atoms by the naked eye, but by using this field ionization microscopy you can actually visualize these atoms. So there is a certain magnification is involved. Fine. To understand this magnification, first we need to understand the effect of shape of on the electric field. Okay. So ideally what we see is that if you have a sphere, this is a particular sphere, and ideally this is having a same radius along all the three directions. So it is r. Okay. And from the basics as we know that if it is a positive charge, if we apply a positive charge, then we can give the field along this sphere as the voltage applied divided by the radius, and this radius is constant, correct, along the three directions. So in ideal case we have a field along this particular sphere as the voltage divided by the radius of that particular sphere. So this is the ideal case. Fine. But our atom probe tip is not the in ideal shape, it is a truncated cone shape, and only the surface has a certain radius of curvature which is equal to the r. But as you move inside the tip surface, you can see that the tip surface is not ideally at the sphere, it is a truncated cone. Fine. So if you apply a positive potential, if you apply a positive voltage, then what will happen, the electric field lines are not same along all the directions perpendicular to the tip surface. Okay. So you can see these electric field lines. In this sphere condition, these electric field lines are same along the radius, along the sphere, along the surface of the sphere, perpendicular to the surface of the sphere. But this is not the case related to the truncated cone. Okay. So and these truncated cone, due to the shape effect, you will have a electric field lines which is not same as the ideal case. Fine. So now here the field which we are getting along the tip, near to the tip, we can give as a V by Kf r. Okay. So V by r is the ideal case, and we are adding up a field reduction factor which is called Kf. Okay. And this Kf value is directly depends upon the Shank angle. What is the Shank angle? If you have an atom probe tip, the half angle is called the Shank angle. This is called Shank angle. Okay, and this kf value is directly depends upon the Shank angle, and smaller is the Shank angle, smaller is the Shank angle or the theta, larger will be the electric field or the concentration of electric field concentration. Larger will be the electric field concentration, results in a decrease in the kf value. Okay, so larger is the Shank angle, lower will be the electric field concentration, larger will be the kf value. Larger will be the factor which is to be needed to take care of the to model the electric field around the tip surface. Okay, so this is one field reduction factor which we need to introduce to mimic the exact condition of the field lines across the tip. So there are other parameters which governs the field reduction factor kf. It is not only the tip shape itself, and also the presence of any flat surface, So usually this atom probe tip, they have been kept in a certain coupon, or we can tell it as a substrate, or the coupon where your sample tip surface is. So this flatness of this surface also is very important contributor for the kf value, which increases the kf value. Okay, and also what we now in the present leap in the present atom probes, as I told you during the history of evolution, in the latest leap, what we do is near to the atom probe tip, we are putting a counter electrode, a hollow counter electrode. This counter electrode is very important to increase the electric field concentration around the tip. That leads to the reduction of the kf value. Fine. So because the kf value is directly related to your electric field concentration around the tip surface. Okay, so the distance between the tip and the counter electrode also can be changed, can affect the kf value of the field reduction factor value. Fine. So the second thing is important thing is the temperature. The second thing is temperature, which is the sample tip surface is kept at the cryo temperature. Yeah, so the specimen is kept at the cryogenic temperature. Okay, so it is between usually we will keep around 25 Kelvin to up to, we can go up to 120 to 150 Kelvin. Correct. So at the sub-zero temperature. Why cryogenic temperature? Because at room temperature, as I told you before, the atomic vibrations will be much higher at room temperature. So it has the dose has to be freeze out. These atomic vibrations should be minimum. So why atomic vibration should be minimum? If your atomic vibrations are minimum at the tip surface, so your gas atoms can actually mimic the atomic terraces or the atomic structure very efficiently. Okay, so your gas atoms can the place of the gas atoms can be fixed at those terraces. Okay, so this directly is related to the thermal accommodation of the imaging gas. And due to the cryogenic temperature, this thermal accommodation or the thermal energy of the gas kBT, correct, is reduced drastically. Okay, and so this will directly affect the lateral velocity of the gas atoms. Okay, the lateral velocity of the gas atoms, thereby which in this is directly related to your resolution. Resolution means the ability to differentiate the two atoms which are present on the atomic which are present on the tip surface by the imaging gas atoms. So due to which this is the region for the cryogenic temperature necessary for the cryogenic temperature. Okay, so now we have introduced the field reduction factor, okay, which is usually it is between the 3 to 8, fine, and it is directly related to the shank angle of the tip surface, tip, and higher is the smaller is the shank angle, higher will be the electric field concentration, and smaller will be the kf value. Okay, now next thing is the projection. Now I have talked about the image projection, correct. So it usually it associated with the magnification, fine. So now you have a tip surface. So as I told you, this is the tip surface, and the tip surface initially it has a certain, assume that it the at the surface it is usually like a sphere, fine, and this is the central point, fine, and this has the some radius of curvature r, correct. Now you are applying a field, and this is your phosphor screen, fine, and the distance between the tip surface to the phosphor screen we assume it as a L, fine. So now you are applying a positive potential, very high positive potential. So what will happen, the gaseous atoms which are present at the tip surface gets ionized, and your field lines which are assumed for a sphere perpendicular to the surface, correct, for a sphere, but ideally it is a truncated cone. So your field lines will not be exactly perpendicular to the surface. So these will have the field lines will go in this direction, like this. Okay, and this change in the field lines, the path of the field lines is directly related to the shape of the atom probe tip. Okay, shape of the atom probe tip. Now further, so now this electric field, whatever the electric field which is induced, accelerates these gas ions. Okay, this accelerates the gas ions, and it hits to the fluorescent screen, and based on the tip geometry or the terraces or the crystallographic orientation, you will get an FIM image, correct, you will get an FIM image. Now so now as I told you, this is a truncated shape, and your field lines are not always perpendicular to the surface. At near to the surface these are perpendicular, but if you go away from the surface your field lines are compressed. So these are called compressed field lines, okay, and this will have a direct consequence to the magnification. How this will show it now. So now assume that this has a radius of curvature, fine. So now assume that if the there is this is the central point which is of the fluorescent screen, okay, you can mark it as a 0 O. Then the atom from this position, so I'll just, so the atoms, if you have a atom probe tip, assume that okay, so you have an atom probe tip, okay, so you have an atom probe tip, okay, and you have a some radius of curvature r, okay, and you have a fluorescent screen. This is the center O and this is your axis, fine. And as I told you, the field lines are compressed towards the this particular axis. This is the central axis. This is the central axis. Your field lines are compressed towards the central axis. Now, if ideally the gas atom get ionized at this location, should go and travel in this direction exactly at the perpendicular, but ideally this is not the case, fine. It goes to along the field lines in this direction, okay, assuming the distance between these two is d, okay. So this is the ideal case, perpendicular to the tip, but it goes along this field line. Your gas atom will go along this field line, which is compressed towards this central axis, okay, and this is mostly related to the tip surface, the field distribution along the tip surface. Now if you project this one at the back side, okay, so you will have a point which is P, which is not exactly at the center of this sphere, okay. And if I magnify this, how it looks, so you will have a this particular case, you will have a R, okay, and from this particular your field line is like this, so you will have a P position. This is, you assume this as a Q position, center position, okay. So now assume that this is your fluorescent screen, this is your center, fine, and this distance is d, and the distance between the tip and N is L, okay. So you know that this R value is very small, it is less than 50 nanometers, it is very small as compared to this L, fine. We can assume that the distance between this particular the distance between the tip and L is L, and the R is much less than L, okay. So this is the assumption, fine. So now if you see the triangles here, if I do the triangular geometry, you can see that the distance, this particular distance is d, okay, and this is your central line, and the position of the gaseous atom at this position from the central line is d. So you can see that this particular case, it is nothing but a triangle, okay, fine. So if you see the, if you get the definition of projection, the position of the gaseous atom from the center and the position of the gaseous atom on the fluorescent screen from the center, that is called the magnification. That is nothing but M projection, which is equals to d by this particular d. So this is particular d and divided by this particular d, okay. So how it is equal? Considering the R is much less than the L, it is directly related to your, so this is, from this distance it is R, and you can see that this particular distance, it is around we can what we can do is, we can write it as a, up to this position, phi R, okay. And this distance is directly, so if you see the triangle, if you see this particular triangle and if you see this particular, then by definition of this particular triangular geometry, what we can write is d by d, M projection, and assuming that R is much less than L, L can be d by d is equals to L by phi R. This is called image compression factor, image compression factor, okay. So based on this we can so this is equivalent by assuming that your R is much smaller than L, okay. So M projection is equals to L by psi R. This is the actual image compression factor, okay. So now there are two extreme cases here. Phi can be either 1. If it is 1, it can be ideally, it means that the tip surface is a sphere because your r is constant, or it is very near to the near to the tip surface. Or the second extreme is phi is equals to 2. It means phi equals to 2 means it's a 2r. So it means the total diameter, it's a flat surface. So either it should be a flat surface extreme or either it should be a sphere. So the phi value is always between 1 to 2. Usually we'll put it as a 1.5 to 1.6 as per the geometry. Fine. So how to calculate this phi? How to calculate this phi? So this also can be calculated by crystallographically, because your atom probe tip, if it is a crystallographically oriented in a particular direction, then whatever you are seeing on the field on the image is nothing but the the image of the terraces of the atom probe tip. So here in the right side you have seen there is an example of for example it is a BCC lattice of tungsten, and you can see that at the tip surface you have a certain atomic terraces which is related to your crystallography. Fine. So as I told you, you can measure, from the distance p, you can measure if you have these gaseous ions are hitting to the fluorescent screen, you are getting the distribution of these spots which is related to the atomic terraces. And if you see this particular FIM image in a top projection, you can see that at the center you have a concentric circles. Fine. You have a concentric circles at each locations here, and these concentric circles you can see that they have a particular symmetry. Fine. And you can index these crystallographic the concentric circles. For example, I can index this as a 110 at the center, and at the right you can have a -110. Now if you project this particular, for example you will have this particular zone is if you talk about 112, you can see that this 112 is here, this is a 110 at the center. Now if you project this particular angle, okay, so you know that these crystallographic directions for a BCC, the angle between 110 and 112 will not change, it is a constant, correct. You can measure by the cos theta crystallographically that particular angle, say if some x degrees. Now if you measure this particular angle theta observed, correct. So this is the theta crystallography which is a x degrees, this is called theta observed, and the phi can be calculated by theta crystallography by theta observed. Fine. So theta crystallography always will be higher, correct. Theta crystallography will be always higher, and theta observed we can measure. So by this we can get the image compression factor which is in between 1 and 2. Okay. So typically for any value of L, so for example if you have a value of L is equals to around 90 mm, so usually 90 mm L, and R equal to 50, okay, and your ICF value if it is around 1.5, so you will get a magnification of 10 raised to the power 6 of individual atoms as compared to the atoms which are present at the tip surface. Okay. So with this you can see that we have briefly introduced the field reduction factor, which is very important for simulating the field lines around the truncated cup, truncated cone or the tip surface, which is KF value, and these values are between 3 to 8. KF is a strong function of the tip shape and the shank angle. Smaller is the shank angle, more will be the electric field concentration, lower will be the KF value, means you are going towards the ideal wave, for the sphere. So KF is smaller, the higher is the electric field concentration, correct. Then we discussed about the cryogenic temperature. What is the need for cryogenic temperature? It actually it decreases the thermal energy of the gaseous atoms. So your the thermal, so it is directly related to your thermal accommodation of the imaging gas on the tip surface. Okay, so it reduces the lateral velocity of the gaseous atoms, which directly controls the resolution. Okay, this particular lateral velocity of the gaseous atom we will talk again when I will discuss about the resolution of the during the field ion microscopy. Fine. And the second important factor is the image compression factor, which is a Xi. This is related to the tendency of these electric field lines which gets bent towards the axis of the atom probe tip. Correct. So this is a direct consequence, this will have a direct consequence on the magnification of the atom probe tip on the fluorescent screen. Okay, and this can be directly, this can also be calculated by the crystallography, with the help of crystallography. So you can measure actual the theta crystallography between the two poles which can be identified based on the symmetry on the field line image, and you can also measure the theta observed from the field line image actual theta observed, and the ratio between the theta crystallography and theta observed is nothing but the Xi, which is called image compression factor. Okay, and which directly relates to the magnification. Okay, so typically your values of L is around 90 mm to 100 mm. Usually we will keep 90 mm to L, and if you have a radius of 50 and ICP of 1.5, you can reach a magnification up to 10 raised to the power 6. That is the power of the field ion microscopy. So we discussed about the projection of ions and also the image formation. Okay, so now I will just briefly introduce the spatial resolution. Okay, so I hope that most of the students or most of the listeners, they have an idea about the resolution of a microscope. Okay, and this is a very simple thing which is related to the Rayleigh's criteria. Correct. So what we can tell is if any two images are just resolvable when the center of the diffraction pattern of one is directly over the first minimum of the diffraction pattern of the other. Okay. So this is the basic criteria which any two objects can be resolved. This is called Rayleigh's criteria. So here I am showing you a nice schematic which is taken from this reference Lumen Learnings, where if you have a two objects, object 1 and object 2, and if you have a small aperture here, and if these two objects illuminates and forms an intensity profile on this particular screen. Okay, and these two objects can be resolved at different positions only when the maximum of intensity of one object overlaps with the minimum intensity of the another. So this is the minimum criteria which is related to your theta minimum, which is related to the resolution limit, all the Rayleigh's criteria. Okay, and this is a nice example, a nice schematic from this particular reference micromagnetic.fsc.edu, where you can see that the usually we see it is in a 3 dimension. So these are termed as airy discs. Okay, so any object if any object if it is if it illuminates, if there are two objects in 3 dimension, so you will have an airy disk where the intensity will be maximum or diffused at the center, and you will have a loss in intensity, again it increases, again it loses. So you will have a certain pattern of this intensity profile. Fine. And if there are two objects which has to be resolved, as I told you, the maximum intensity of one object should overlap with the minimum intensity of the another object. Fine. So this is the Rayleigh's criteria. So what is the resolution, spatial resolution in terms of FIM, field line microscopy? Correct. So that this also is very important. So in field line microscopy, the definition or in FIM is the size of the smallest image spot on the screen on the fluorescent screen, means size of the smallest image spot on the fluorescent screen, which is related to the gaseous atoms or gaseous ions which are projected or which are hitting to the fluorescent screen. Okay. So there are three major factors. There are three major factors which directly influences the resolution in film. Okay. So what is those three factors? One is size of the ionization zone, second one is the lateral velocity, and third is position uncertainty. Fine. So what is the size of ionization zone? Size of ionization zone is directly related to the is related to the each spot, the spot which is formed by the successive impact of continuous flow of ions projected on the fluorescent screen or detector. Okay. So this particular thing is directly related to the ionization zone. Okay, which is exactly above the sample tip surface. So there is a certain ionization zone exactly above the sample tip surface, and this size of the ionization zone directly influences the resolution in the film, which is directly proportional to the distance between the gaseous atom and the tip surface. Okay, how it is that? So we will discuss about this. So and the second term is called the lateral velocity. Okay, so how this lateral velocity? So lateral velocity is directly related to your trajectory aberrations. Okay, we'll discuss about this trajectory aberrations in the next class. Okay. So this is I'll just introduce these terms so that you will be familiar with these three important terms. The another one is the position uncertainty. Remember that these gaseous atoms we are talking at the atomic level. Okay, and it creates an image of the atomic surface of the surface. Fine. And this position uncertainty is directly related to the confined volume, and of at on the tip surface, Okay. So this this is related to your position uncertainty. Okay. So we'll come to these all the three major factors in the next class, where I will explain briefly about these three important factors which influences directly the resolution limit of the FIM. Okay. So with this I will end this class, and I hope you understand the how the imaging gas atoms in the film and on application of the electric field we can actually magnify the structure of the atom probe tip on a fluorescent screen, and this magnification is directly estimated directly done by the estimation of image taking care of image compression factor, and also the distribution of electric field line is also directly can be mimicked by the putting of KF, which is a field enhancement factor, KF value, okay, which directly depends upon the Shank angle of the atom probe tip. So with this I will end this class, and we will meet in the next class and discuss about the more details related to the spatial resolution of FIM. Thank you.